The next speaker is already here. He will present in English. Please welcome Thomas Krebs from his technology consultant at Pink Thermosysteme. He will speak about yield sintering of molded power modules on heatsinks for high-performance electric vehicle applications. Very interesting topic, I guess.
Yeah, thanks for the kind introduction. The monitor here in front, it's the wrong. It's just the Productronica logo. Perfect. Thank you. Yeah, thanks for joining. I hope you did join also the talk of Mr. Fehoff because a lot of his topics he already discussed. Basically, I will use also in this presentation as we are talking about volume sintering of molded packages to coolers. And he talked already about sintering of packages to coolers and explained about advantages and disadvantages of soldering versus sintering, and we will go to that one too. But first of all, I will have a short introduction of the Pink company, and then we will have a quick look to some of the trends for BEV inverters, and then checking about the sintering of packages to cooler. And then I do the introduction of the equipment which is basically used for this one at our customers. But first of all, allow me to start with really a short introduction of Pink. If you don't know our company, we are located in Wertheim. We are a family-owned company having customers around the world in the automotive and also industrial electronics, as well as semiconductor and pharmaceutical industry. And the product we are developing and manufacturing are also listed here on that screen. We are very strong in vacuum-assisted soldering for power electronics in particular, for sintering also in power electronics, for low pressure plasma, for cleaning and surface activation, for instance, but also for vacuum drying systems. The size of the company is about 200 people, and the company was founded in 1979, so we have quite a history. And for us, what is very important is basically the innovation. So we have participated the Top 100 Innovation Award 3 years in a row, and by 2025 we have won basically that Top Innovation Award, and you can see here on the screen the head of our R&D together with Mrs. Pink receiving that Innovation Award. But now let's start with the real topic I want to talk about. It's about power electronics in cars, in particular in BEVs. And when we have a look to it, I just listed some of the what I think major trends when we have a look to those kind of modules. First of all, when we have a look to automotive industry, which is key, is of course modularity and scalability of such kind of things. That is a big help for all of the OEMs. Unfortunately, I will not talk about this one by today, but we will have a look to the more, let's say, also hardware-related items when we're talking about reduction of volume, which means it's an increase of power density. And increase of power density means also I need to get rid of the heat I have then created in a smaller area. We have shorter thermal paths because all of the power electronics manufacturers, they try to get rid of the heat very fast and very efficient. That also means you transport then the thermal energy to a next layer, and you need to make sure that you can also remove it from there. And at the same time, we talk about lifetime and reliability. Just think about you are driving your car 2 o'clock in the morning in an area, not too many people, and your car stops. I mean, that's the worst thing what can happen to you, and that is what all of the car manufacturers try to avoid, that you have really a breakdown of your car and you cannot drive further. So lifetime and reliability is key, of course, for the OEMs, but also for us as consumers. One of the trends we also see, we have, of course, different kind of topographies which are used by today, like the 3LT and CP, for example, which have a higher efficiency. At the same time, we have here a graph on the screen, and important here, we have, of course, here's the power density, and here we have the year in the scale. Important basically to me is or are the colors. The green color basically stands for silicon chips. We have the brownish here, which is basically thick, and the blue ones, that is gallium nitride. And what we can see is that when we have a look to it and to the history, of course, in the mid of the 2010s, we see more and more SiC-related ones, SiC-related inverters, and nowadays already gallium nitride is upcoming, and with the use of this wide band gap, we of course have a higher switching frequency, and we also result in higher current density. But higher current density, higher switching frequency means also we have created a bottleneck on the thermal performance of the inverter. We need to get rid of the heat. I had by yesterday a discussion with a tier 1 manufacturer of inverters, and they said they have a customer, they have a request for an inverter which is it's the size of your hand, and they want to have 12 kilowatt power on this one, and you need to get rid of the heat you basically has as an energy loss in order to make your device durable. So what you can do, of course, you can use alternative kind of packaging technologies. We have heard about from Mr. Feo about the sintering of the chips. But when we have a look to the package itself, we can of course go also to double-sided cool packages, which would be a help, or we can also go to power packages sintered to directly to cooler. Mr. Feo has already shown a little bit of that one. I tried basically to do quite something similar. I tried to compare the different kind of materials, and basically we have here in the upper line, I basically used the SAC solar. Here I used silver sinter, and here I used copper sinter. And I had a look to different kind of properties of the material, like for instance the CTE, the process temperature, the usability at higher temperature, and so on. And basically, red means it does not fit so well, and green means it quite fits well. And what we can see is that we have a lot of green for silver sinter, but also for copper sintering. So in terms of compatibility to cooler sintering, of course, the silver sinter layer or the copper sinter layer would technically be, of course, of benefit. So why I should choose sintering for the interconnect between my power package and my cooler? First of all, we have heard it's about higher reliability. We have a superior thermal management because we have a better thermal conductivity of that interconnect. We have a wider operation temperature range as these materials are stable clearly above 200 degrees C, whereas solder is typically its limit at 125, maybe 150 degrees C. And if you just recall that one slide where we have seen the wide band gap introduction inside of these modules, when we have a look to that one, and when we can see the trend and tendency clearly to SiC and gallium nitride, then this one is of course a future-proof technology. You prepare yourself with this kind of technology for the next kind of inverters which will come up. And another point is, to me, basically it's a technological differentiator because it's something unique. Not everyone can do by today a sintering of a molded package to cooler. That is something which is not so easy. It's a little complicated. You need to know about some of the details, so it's not mature. Of course, Mr. Feo also referred to that one. A lot of things are done on solder in order to push the limits. For instance, you introduced the inner load as an alternative. We also can reduce the shrinkage void on the large area soldering in order to make such kind of devices longer living, and we also can have optimized structures or devices in order to have a perfect heating and cool down of such kind of devices in order to minimize also the stress I create inside of that interconnect during manufacturing. But let's go back to the module sintering. Why we do that? As I said, reliability is key. And when we have a look to the today's technology, we're using sometimes even TIM, so thermal interface material, which has an issue of pump out. So the thermal performance of that kind of technology over the time will degrade. What Mr. Fierf also already introduced is, you may can see a little bit, we have here a soldered layer here, and after thermal cycling, we can also see here a crack. So, and for the thermal interface material, if we have a look to that one, we also have the issue that the thermal performance of that material is not that good. And when we have a look to the requirements for BEVs, of course, the BEVs, the requirements nowadays are more demanding, higher lifetime we have discussed, improved thermal paths are needed. We have, when we have a look to sintering compared to the use of TIM or soldering, we have a better thermal conductivity. And when we have a look to it, our belief is that the sintered packaging or sintered interconnect technology for power packages is a technology which can quite help you quite a lot, and is a technology which will come. However, when we are going to the sintering of such kind of molded packages, we have that mold which is temperature sensitive, it doesn't like pressure. You can have failures which you can do or which you can see after processing, and you need to take care of them. So basically, you can have, after processing, isolation failures. The electrical performance might be not sufficient. We have, as I said, the mold compound does not like high temperatures, high pressures. And your coolers are, when you have a look to them, first of all, they're never even flat. Yeah? And when you heat them up, they start to warp and wrinkle. And you need to take care about that one. When we have a look to the process and the equipment, it has to be scalable, because just think about, you are a supplier of an automotive, and you come around with your first sample, with the A sample, and you're using a technology in order to manufacture that. And then you go to B sample and you go to C sample, and you have to change technology because the size is different, and you are getting more mature and you're changing the equipment. Then basically you have the issue that you need to demonstrate that this kind of technology you are using now in order to manufacturing the B sample and C sample is equal to the A sample, for instance. So changing tooling and changing processes in automotive is possible, but it's a kind of a discussion you will have then and need to demonstrate it's really the same thing. And also when you start such kind of a production, you may not run at the first day in full scale, and you may have different kind of products you want to manufacturing on the same machine. So means the flexibility for that equipment has to be there, otherwise you have to invest in additional equipment, which means additional costs, and this one is a thing we typically do not like. We also need to be cheap, so means we need to have short cycle times. It would be great if we can process devices in parallel. We have a need for high quality, for repeatability, and of course we need to have an automated system. When we have a look to the solution we thought about it at Pink, we have developed the SIN100 multi-drive for exactly this kind of application. We have that developed for sintering of molded modules to coolers. And as you can see also here on that picture, it's a modular system, and we will have a look to that in more detail on a later slide, where we can combine different kind of modules based on the need of your production and of your product, basically. We talked about device failures which can happen. So we have taken care about that one by customized tooling. We have introduced in that machine a temperature and pressure control for the single units, so that we make sure we have the right parameters for the sintering. We have short cycle times, because we can do a fast heat up of the cooler, for instance, and we control the pressure quite homogeneously all over the parts. And there is also taken care of some minimal thermal distortion between your package and the cooler. So this is one thing I have introduced before. You may have failures or imperfection inside of your device. You may have different thickness of sinter layers. You may have a warpage on your part. You may have complicated 3D structures on the bottom of your part. And basically, you have to take care about that one. You want to make sure you want to have, at any time, no matter how your device is looking like, it's the same pressure everywhere. Yeah, and the machine has to take care about that one, that I have the same temperature, same pressure at any time, no matter how the part is shaped, and that is done in our equipment. We have thought about some, I think, really smart features of that machine, which is taking care about that one. And here, coming back to the modularity of that equipment, basically, I mean, when you start at R&D and do your first trial, you don't want to have a machine which is basically made for full-scale production. Yeah, you don't want to invest in that one first. You may start with a single sintering drive, having the same technical features of the sintering, of the large-scale sintering machine, but it's basically only the sintering equipment itself. That is basically what you need. And then you can scale that upwards to sintering and cooling up to a full line, and that basically ensures that you always use the same kind of technology for assemble up to high volume production. So you don't have a break inside of the logic of your manufacturing of the parts. And furthermore, that machine also give you a high degree of flexibility. We have inside there 4 drives, so you can basically manufacture 4 parts at the same time. And the tooling you might need for that one, that is toolless exchangeable. So you can do a fast changeover. You can have a mix of different kind of products you can basically process inside of that machine. And as I said, it's modular. You can expand that and can add options like additional cooling, soft cooling, preheating modules, and also formic acid is of course possible to be used in that machine. And for high volume manufacturing, as I said before, you need to make sure we have short cycle times. Therefore, we have a special kind of a heating device inside of that machine in order to heat up quite fast. And as I mentioned earlier, you can process up to 4 devices at the same time in order to increase your throughput. And the quality is ensured by a uniform temperature control. And as I mentioned also earlier, we do have the opportunity, as we are using vacuum-tight chambers, we can use also nitrogen and formic acid inside of that equipment. And that is not so unimportant. Just think about if you want to do later on a sintering with copper paste, you would have a need for protective atmosphere or even for a reductive atmosphere. But also by today, when you have a look to such kind of devices, sometimes they have copper pins which are not tin finished, for instance, and you don't want to have them oxidized because these are typically your signal pins. And if they are oxidized, you may have then an issue with the signal transfer from your device to your controller. And it's a fully automated inline system, of course. We can sinter also different designs. You can have, for instance, pin fins, you can have water channels, you can have different pitches between the molded packages. All of that is possible. And this is an example on how such kind of equipment can look like, where we have at the beginning, of course, a conveyor to bring the parts inside of the machine. We have a handling module, we have a preheating, and then followed by, in black color, by the sintering module. You can have then a soft cooling or cooling module and a handling module and a conveyor again. And last but not least, I tried to explain that before, but that equipment has a great flexibility in terms of the toolings and also in terms of the processes I can do inside of that. So basically we have developed that machine for the sintering of the power packages to the cooler. But it can do even more. Of course, we can do sintering power package on cooler using the multi-stem tool as is the standard in that machine, or we can use a weight bar. But we also can use that machine in order to do die attach with our soft tool, which is a very flexible equipment, but also with a multi-stamp tool. We can do even clip attach in that machine. And we also can sinter double-sided cool modules, then we have a combination of different toolings inside of that equipment. So having said that one, I am good in time, I think. We come to the end of my presentation, and I just could strive a little bit on that equipment. And if you want to know more about that technology, what you need to know, what it can do for you inside of your production, how flexible it is, then just visit us. We are at Hall A4, booth 225. You are welcome to visit us, and we are happy to answer your questions and give you some hints. And yeah, thanks for your attention.
Thank you, Krebs. Do we have any questions from the audience? Short notice? One, okay.
Thank you for the presentation. Quick question. You talk about cycle time. What typical cycle time do you have for such a device you showed here?
Yeah, I mean, basically, as I said, you can have 4 coolers at the same time in the machine. And basically, the cycle time is more or less, I would say, defined by the sintering material you are using. As you know, you can have sintering material which needs a little bit more time, and others which we can have a short processing time. So, but if we have a look to the items which are basically limited by the machine, you need to heat up your cooler, for example, and you need to build up your pressure. That is done within seconds. And then we just need to wait for the sintering paste that it does its job. And so more or less, I would say it's your sintering time of your material plus maybe 20 seconds you need to add in addition. And that we divide by 4, so we are potentially at plus 5 seconds together with the sintering time, right?
So for one cooler, you need?
For one cooler, we need, now you need to calculate. I make it simple for me. Let's say we divide 50 seconds.
Okay.
Thank you very much. Any other questions? We have a little time, if there are any. No? Then?
Thanks a lot. And
everything.
you're welcome to visit us at our booth in Hall A4. Thank you.
Thank you very much.